Hello wonderful person, this is Anton, and today we're going to discuss a relatively new study that investigates early impacts on planet Earth, and specifically devastating impacts involving enormous asteroids and the effects all of this would have not just on the planet and the climate on the planet, but also early life. And in this case, the study we're going to be discussing actually discovered evidence for an enormous impact approximately 3.2 billion years ago, with an actual asteroid being at least 200 times more massive than the one that killed the dinosaurs. And so let's discuss this event, referred to as S2, and of course the effects it potentially had on all of the early life that existed 3.2 billion years ago. But I guess let's start with the obvious. Back in the days, when the Earth was still very young and when life was still developing, we have a lot of signs of various large impacts, whose evidence is present in a lot of different deposits, but whose evidence is also visible on the surface of the Moon. And previous studies examining the so-called Archean Eon found rocks exhibiting evidence of at least 16 major impacts, with each of the asteroids being at least 10 kilometers across. In comparison, the asteroid behind the dinosaur demise, that happened 65 million years ago, was maybe just a little bit smaller. And though we have an idea of what happened 65 million years ago and how it potentially affected life, we obviously have absolutely no idea how all of this affected Earth billions of years ago. And specifically, how it affected the habitability of the early Earth and all of the bacterial life that existed on the planet for at least a few hundred million years. And that's of course a really important question because statistically these large impacts seem to have happened at least every 15 million years during those first 2 billion years of the existence of planet Earth. And so between 3.5 billion and 3.2 billion years ago, we actually have direct evidence for an impact at least every 15 million years. And here we're talking about a really large impact. Basically a dinosaur killer asteroid striking the planet and very likely causing extinction-like events. Yet we know that life persevered and it survived. And so it most likely had some effect on life, but the question is, why did it not go extinct? Or I guess a much more direct question is, what actually happened to early life when these events occurred? And so today we're going to be discussing this one study that found a direct evidence of an enormous event with all of the geological evidence showing us what most likely happened. And it's actually a study by these wonderful people, except I guess the guys with the rifles. Those were mostly for the protection because this was in some really exciting regions of South Africa. This is a study by Nadja Drabon and her team focusing on new geological discoveries coming from the Fig Tree Formation in South Africa, roughly located in the region you see right here. And so here they discovered something really unusual. Although technically it was not unusual, it was kind of expected, but still very bizarre. It was basically this: a tremendous amount of spherules from an ancient Archean impact layer that was formed from various types of molten debris, the result of this asteroid's impact. And based on the amount of spherules and the thickness of the layer, this implied an enormous event. Very likely some kind of a chondrite asteroid, at least 37 kilometers across, but possibly as large as 60 kilometers. So at least 6 times larger in size than some of the previous events, and more importantly, at least 200 times more massive. And such an enormous impact would have very extreme effects, much more extreme than the collision from the asteroid 65 million years ago. Here obviously we expect a tsunami and the release of a lot of dust into the atmosphere, potentially darkening the planet for at least several years, but we also expect partial evaporation of the ocean and the heating of the atmosphere to some ridiculous temperatures. So for example here they discovered unusual hexagonal salt crystals that were most likely deposited as a sudden evaporation event resulted in all of the ocean water basically turning into steam, which then formed these unusual crystals that became inclusions inside the sediment. And this was actually a sign that this impact very likely overheated the surface and basically boiled off a lot of the ocean on the surface of the planet. In this case, the oceans on the planet very likely lost anywhere from a few meters up to tens of meters because everything was just evaporated due to the extreme heat. And that actually includes the atmosphere. The atmosphere was probably at least 100 degrees Celsius for at least some time, but most likely much higher than that, with the additional effects from this ridiculous heat dramatically increasing the weathering and the erosion on land, which is also visible in some of these deposits. And so essentially, for at least a few years, the conditions on the surface seem to be hell-like. Pitch black, overheated atmosphere that very likely blocked most of the light, and the atmosphere that was also filled with a lot of toxic gases and a lot of other materials that were basically released during the initial explosion. And so in these conditions, we obviously don't expect any modern life to survive, yet ancient life did just fine. As a matter of fact, even photosynthetic life that was expected to basically become extinct somehow managed to survive. But that's not really the conclusion from the study. The conclusion seems to point at almost the opposite. Not just survival, but actually extreme proliferation of life following this event. And so basically, right after the collision, one of the first things that happened was a tremendous tsunami. And this giant tsunami did something somewhat unusual. It actually ended up mixing a lot of minerals and a lot of metals coming from within the ocean with the rest of the water. So for example here, some of the previous deposits seem to suggest that a lot of iron metabolizing bacteria that would actually rely on iron for basic photosynthesis was not that successful. This bacteria would basically convert carbon dioxide into sugars by trying to get some of the dissolved iron in the water and by using basic photosynthesis for survival. Most of this was happening in the top layers of the ocean where there was a lot of light. But these top layers did not really have much iron, so back then this life was not particularly successful. But right after this enormous impact, all of the iron from deep in the oceans and from the crust suddenly became released into the oceans, with the following tsunami mixing everything across the planet. And so this tsunami very likely brought extremely iron-rich water to all of these upper layers in the oceans where photosynthetic life would then use it later on. And so even though initially there might have been some life here, specifically some life using photosynthesis, and right after the impact there was probably no major survivors in this layer, because now we had so much iron available in every layer of the ocean, within just a few years, once conditions improved, it looks like there was a major bloom of new photosynthetic life that seemed to have spread across the planet really quickly. And so these horrible conditions that lasted for maybe a couple of years were actually replaced by something entirely different. A blooming biosphere that recovered extremely fast, with all of the microbial life potentially becoming widespread everywhere on the planet. Especially these microbes relying on iron, which seem to have added to a tremendous amount of biomass during this time. And this is exactly what was discovered in these sediments by studying carbon. Essentially, right above these spherules, there were signs of huge amounts of organic carbon that was very likely formed by these early photosynthetic bacteria. And all of this was very likely the result of this huge impact. The impact that seemed to have released a lot of stuff on planet Earth, suddenly giving life something to eat. So here we had signs of iron, but also signs of phosphorus that seem to have been ejected during this event. And as I mentioned, tsunami mixing everything in the oceans. Which of course implies that these giant impacts, despite being detrimental for the first few years, were extremely likely followed by sudden explosion of life and possibly even rapid evolution. Although here it's unclear how the life on the surface managed to survive. Obviously the life deeper in the ocean survived just fine, but the microbes on the surface were potentially not as lucky. Yet somehow they did survive and bloomed afterwards. And so here we essentially have direct evidence for major massive impacts on the planet, and impacts that very likely resulted in a major biosphere evolution, mostly through the increase of nutrients and various types of metals essential for bacterial life. In this case, the researchers even refer to this as a kind of a giant fertilizer. 360 billion metric tons of phosphorus released into the oceans, and 10,000 cubic kilometers of vaporized rock circulating around the planet, eventually turning into more nutrients. Although in this case, it's fair to assume that it wasn't just phosphorus and iron. It was very likely a lot of other important stuff, including potentially nitrogen, that's crucial for a lot of life to survive. Although here there's no direct evidence yet. There is, however, intriguing evidence for something super unusual. Because of the shift in carbon isotopes, it basically suggests an entirely different type of metabolism that existed right after this event compared to previously. So in essence, it shows us that following these events, despite initial blunders, life reaches new heights, evolving something new in the process. But obviously, it will take at least 2.5 billion years for more complex life to start appearing. And that's because the chances for more complex life to survive this is of course not very high. we basically only expect microbes to be able to survive something like this. And so anything more complex, or I guess anything that's multicellular, would probably not survive these events, unless I guess it was hiding somewhere on the bottom of the ocean. But anyway, still a super exciting discovery, and I guess a really important analysis of what happened to our planet early on, and how these impacts potentially helped the life evolve over time, but also a really important reminder that once upon a time the collisions were extremely powerful, and we're basically kind of lucky now, because these collisions are extremely unlikely to happen. But we'll actually talk a little bit more about these impacts in some of the future videos, and you can find even more stuff in some of the previous videos in the description. On that note, thank you for watching, subscribe, share this with someone who loves learning about space and sciences, come back tomorrow to learn something else, support this channel on Patreon by joining a channel membership, or by buying the Wonderful Person t-shirt you can find in the description. Stay wonderful, I'll see you tomorrow, and as always, bye bye.